In this module, we will consider gravity. Our primary experience with gravity is with the force that pulls everything down toward the surface of the Earth with a uniform acceleration of 9.8 meters per second squared. But for over 100 years now, we have understood gravity to be the reaction of space and time to the presence of matter and energy. This reaction is that space and time become curved, causing everything passing through it to follow specific paths. In the words of John Wheeler, matter and energy tell space and time how to curve, while space and time tell matter and energy how to move through it. This is our best understanding of gravity, known as general relativity. But even before Einstein's theory of general relativity, Newton understood that gravity extended beyond our experience at the surface of the Earth. Newton proposed that any two bits of matter experience a certain force of attraction which underlies what we experience as gravity. We now know that Newton's description of gravity is not correct, but it is what general relativity predicts so long as matter does not become too dense or move too fast. Newton's law of universal gravitation is, in fact, an excellent approximation in most situations, and we will explore it in some depth. Newton's law of universal gravitation says that any two masses attract each other with a force that is proportional to the product of their masses, inversely proportional to the distance between them, and is directed along a line connecting them. We can express this mathematically in the following form. In this, m1 and m2 are the masses of the individual point masses. R is the distance between the point masses, and capital G is Newton's gravitational constant. Finally, probably the most difficult part of this equation to get right is the unit vector, r hat. R hat is the vector of unit length, and it points in the direction radially away from the mass causing the force and toward the mass on which the force is acting. So, for example, r hat 1, 2 is the unit vector pointing radially away from m1 towards m2, and it is the unit vector of importance for the force acting on m2. Similarly, r hat 2, 1 is the radial unit vector pointing radially away from mass 2 towards mass 1 and is the vector of relevance for the force acting on mass 1. But we know that Newton's law of gravity says that masses attract each other, and this is the reason there's the minus sign in the equation. And what is really important is to consider minus r hat. This is the vector pointing in the direction in which the force acts. That is, the force of mass 1 on mass 2 points in the direction of minus r12, and the force of mass 2 acting on mass 1 points in the direction of minus r hat 21. Let's consider an example here. Given three masses, m1, m2, and m3, all of equal mass, 0.3 kilograms, find the gravitational force of m1 and m2 on the third mass, m3. To begin, we consider each pair of masses. First, we consider mass 1 and mass 3, and the force between them is given by g m1 m3 over r13 squared. That's the distance between those two masses. And the vector of relevance is minus r hat 13. This vector is pointing towards m1 from m3. And in terms of our I hat, j hat, and k hat, in this case, we can write it as minus I hat. The second force is between mass 2 and mass 3. It has a similar formula, but it now involves the distance between mass 2 and mass 3. And the vector of relevance is minus r hat 23, which points radially from m3 towards m2. And minus r hat 23 can be written in terms of unit vectors. If we notice that the angle between minus r hat 23 and the horizontal is theta, then we can compute the angle theta and the components of the unit vector. Remember, the length of r hat 23 is 1, and so minus r hat 23 is minus 0.6 I hat plus 0.8 j hat for the case of this particular triangle. The total force acting on mass 3 is just the vector sum of those two forces, so we simply add them together, substitute in for the unit vectors, and then group together the components in the I hat and the j hat direction. And finally, plugging in numbers, we get the magnitudes of the components in each direction. Newton derived his equation for universal gravitation essentially by guessing its general form, and then verifying specific aspects of it by comparing with astronomical observations. Experiments on Earth were not sensitive enough at his time to measure the force of gravity between two laboratory scale masses. This meant that Newton couldn't determine his gravitational constant g. And while it was clear that the gravitational force should be proportional to the product of the masses, he couldn't confidently guess the dependence on the distance between the masses. Now, it turns out that we can figure this out by using our knowledge of the moon. Eratosthenes, back in 240 BC, was able to determine reasonably accurate values for the radius of the Earth and for the distance to the moon. And after that time, people were able to come up with even better estimates for these distances. Together with the equation for centripetal acceleration, this was enough to show that gravity was roughly an inverse square law. Let's see how this worked. If we consider the moon to be in a circular orbit around the Earth, then the moon is held in that circular orbit by a centripetal force provided by gravity. So the mass of the moon times the centripetal acceleration must be equal to the gravitational force between the Earth and the moon, acting at the distance between the Earth and the moon to some unknown power alpha. Notice that the mass of the moon appears on both sides of the equation, so we can cancel this out. If we also divide both sides by the distance between the Earth and the moon, then the left-hand side essentially becomes the angular velocity of the moon in its orbit around the Earth. And we notice that we know everything in this equation except the mass of the Earth times Newton's gravitational constant. To deal with these two terms, we note that the gravitational force on an object of mass m on the surface of the Earth, m times g, has to be equal to the gravitational force acting between the Earth and that mass. We can use this to eliminate the mass of the Earth times Newton's gravitational constant from the previous equation. The result gives us a relationship between the angular velocity of the moon around the Earth, which we can rewrite in terms of the orbital period of the moon, and the radius of the Earth, and the distance between the Earth and the moon, and the gravitational acceleration on the surface of the Earth. We can rewrite this formula a little bit, and then take the logarithm to find an equation which allows us to solve easily for the coefficient alpha, which is the power to which the distance is raised. Alpha turns out to be roughly 2, which gives us the inverse square law for gravity. To further check his law of universal gravitation, Newton was able to compare against Kepler's laws of planetary motion. Kepler derived these laws long before Newton was even born, based on very detailed observations of the positions of the planets in the sky. His first law states that the orbit of a planet is an ellipse with the sun at one of the two foci. The second law is that a line segment joining a planet and the sun sweeps out equal areas during equal time intervals. And the third law is that the square of a planet's orbital period is proportional to the cube of the length of the semi-major axis of its elliptical orbit. Using the first law, Newton was able to use his laws of motion and his universal law of gravitation to show that only an inverse square law of gravity can yield a closed elliptical orbit. If we draw a diagram illustrating Kepler's second law, we see that a planet at a position vector r from the sun moves a distance dr during some particular time interval. The area swept out during that time is given by the yellow shaded area. We can express the area of that shaded region dA in terms of the cross product between r and dr. Remembering that the area of a parallelogram formed by two vectors is equal to the cross product of those two vectors, we see that the area of the shaded region is given by 1/2 of the cross product between r and dr. We can then relate this directly to the angular momentum of the planet orbiting around the sun. This means that the time rate of change of the area being swept out by the planet as it moves around the sun is directly proportional to the orbital angular momentum of that planet. Now, if we consider the torque produced by gravity on the planet as it orbits around, we find that this vanishes because the force of gravity is parallel to the moment arm r. So, putting this all together, we notice that the force of gravity on the planet produces no torque, and therefore the angular momentum of the planet will remain constant. That means that the rate at which area is being swept out is going to be a constant. So, Kepler's second law turns out to be nothing more than a restatement of conservation of angular momentum. We've already seen Kepler's third law when we examined the orbit of the moon around the Earth. In that case, we assumed that we had a circular orbit, and we came up with the relationship between the square of the orbital period and the cube of the radius. In general, when we have an elliptical orbit, this changes only slightly, but we find out that we can relate the square of the orbital period to the cube of the semi-major axis through a combination of the masses of the two objects which are in gravitational attraction. Consider now the gravitational attraction of an extended object. In this case, the force between a thin hoop of mass capital M and radius capital R on a test point mass M0 located on the axis of symmetry at distance x0 from the center of the hoop. We compute the total gravitational force of the mass capital M on the test mass by summing up all the little contributions of little bits of mass around the perimeter of the hoop. First of all, consider a bit of mass at the very top of the hoop, dm. We can easily calculate the distance between the test mass and that little bit of mass dm, and calculate then what the force is between the test mass and that little bit of mass. It has a direction, of course, directly towards that little bit of mass dm. Now we can do the exact same thing for another bit of mass dm on the opposite side of the hoop. It'll have a force with equal magnitude, but the direction will be different. However, notice that the components of those two forces, which are perpendicular to the line of symmetry, are going to cancel out. Only the parts of the gravitational force parallel to the axis of symmetry are going to remain when we add these two pieces of force together. Now, for any bit of mass on one side of the hoop, there's going to be a corresponding bit of mass on the opposite side. So in all cases, only the parallel components of the force matter in calculating what the gravitational force is going to be. So, knowing the angle theta between the axis of symmetry and the direction of the force at some point, we can calculate the parallel component of the force. It will act in the minus I hat direction here. And we can then integrate these up all the way around the hoop. Now, fortunately, all the components of the integral are constants, and we simply have to sum up over all the different pieces of mass dm, which just gives us the total mass. And of course, the perpendicular components all integrate to 0. And what we find when we do the integration is the following formula for the gravitational attraction of a hoop for a point lying on the axis of symmetry. Now, be careful, this only applies for points along the axis of symmetry. If we move off by any distance, we need to calculate a completely different equation for what the force would look like. And in that case, without the symmetry of being on the symmetry axis, the calculation becomes much more difficult. More interesting is what happens if we consider the gravitational attraction of a thin spherical shell of mass m and radius r. Let us consider the gravitational force on a point mass at some location x0 along the x-axis. We can compute this by breaking up our spherical shell into a number of thin hoops, each one behaving very much like the thin hoop in the previous example. So, we can realize from the symmetry of the problem that we only need to compute the components of the force which are parallel to the x-axis. With a little bit of geometry, we can easily compute the distance between any point on the hoop and our point x0 where we want to evaluate the gravitational force. But, unlike the previous example, our hoop is not a simple thin hoop. Rather, it is part of a spherical shell. This means that we must be careful about computing the area of this little bit of spherical shell. Again, we can use a little bit of geometry to do this. We can define an angle theta marking the beginning of our thin bit of shell, and another angle d theta which denotes the width of the thin bit of shell, making the width of this bit of shell r times d theta. So, this means that the area of the hoop is the product of its circumference given by 2 pi times its radius y and multiplied by the width of the little area, which is d theta. And given the relationship between x, y, and the angle theta, we can immediately see that y times d theta is simply dx. This allows us to compute the mass dm of this particular ring of matter. Putting this all together and integrating over all of the rings of matter that make up the thin spherical shell, we find the following very interesting result. If the gravitational force of the thin shell acts on a point mass inside of the shell, then the integral reduces to 0 and there is no gravitational force. On the other hand, if the mass is outside of the thin spherical shell, then we get a non-zero result. In fact, if the test mass is outside the spherical shell, then the gravitational attraction of the entire shell is the same as if all the mass were concentrated at the center of the sphere. On the other hand, again, if the test mass is inside the spherical shell, then no gravitational force is exerted on the test mass by the thin spherical shell. We know that a gravitational force exists between any 2 point masses, And we have seen that we can compute the gravitational force on a test mass due to a collection of point masses or even an extended distribution of mass. Now, if we move the test mass to a new location, we get a new gravitational force. But was there no gravitational force at the new location before we put a test mass there to measure it? And is there no gravity now at the place from which we moved the point mass? It turns out that it makes sense to talk about a gravitational field that exists in space even if there are no test masses present to experience a force from that field. The value of this field is simply the value of the force acting on the particle divided by the mass of the particle. The gravitational field G simply represents the gravitational acceleration that an object will feel due to the gravity of some other distribution of mass. For example, for a point mass, we simply get that the gravitational acceleration is minus Newton's gravitational constant times the mass of the point mass divided by the distance to the point mass squared, and the direction is given by r hat. Let's consider the previous example we looked at for the gravitational force, but now consider finding the gravitational field of mass m1 and m2 at the location of mass 3. In this case, mass 3 no longer matters. The gravitational field due to mass 1 at this location is going to simply be given by the following formula, where the vector nature of the gravitational force is going to be given as before. And we can do the same for the gravitational field due to mass 2. Again, the direction of the vector field is going to be in the same direction as the previous force. We simply don't have to include the mass m3 in the calculation. So we put the pieces together again as we did before, and we can easily calculate the gravitational field at position 3. And if we multiplied our result by the mass of m3, we would get the gravitational force. But here, what we want is the gravitational field. Now, our gravitational force, the force between two masses, turns out to be a conservative force. As such, we can define a gravitational potential energy between 2 point masses. Recalling that the change in the potential energy is minus the work done on the particles, we can express this as minus the integral of the gravitational force along some path. Well, in this case, it turns out that our r hat vector dotted with ds is simply our infinitesimal change in the radial direction. This simplifies our integral considerably, and we find that we can calculate the change in the gravitational potential in the following way. And this means that we can define a gravitational potential energy between 2 point masses as simply minus Newton's gravitational constant times the product of the masses, and divided not by the square, but by the distance itself between the 2 point masses. Notice that this is the potential energy, not the force, and it is a scalar quantity. There is no direction associated with this, and therefore it's an easier quantity to deal with. The other thing to notice is that, like any other potential energy, we have the freedom to choose where we set this potential to be 0. And in this case, this definition uses the idea that the gravitational potential goes to 0 when the 2 point masses are infinitely far apart.